Hello and welcome to lecture 33 of analog integrated circuit design. At the end of the previous lecture, we looked at cascoding, that is using a common gate amplifier as a possible way of increasing the output resistance of a transconductor and thereby improving the DC gain. So, we will start with analyzing this cascode combination in a little more detail and then apply it to our single stage op amp to come up with an op amp that has a higher DC gain. Okay. A cascode is a combination of common source and common gate amplifiers. Now, the lower device does not have to be a common source, it can just be a current source, a fixed current source. Even then the output resistance would be improved. Okay. So, this could be, let us say V bias. If it is just V bias, it is a current source, and if it has V bias plus Vi, it is a common source amplifier, and the output resistance in either case would be GMC RDSC RDS1 plus RDSC plus RDS1. It is dominated by this term, and we will frequently use that as an approximate value of the output resistance, because it is going to be definitely much more than either of these two terms. Okay. Now, the advantage with this is that you can get an order of magnitude increase in the output resistance without an increase in length. Increasing the transistor length would slow down the circuit, whereas this does not appreciably change the circuit. Okay. Now, where can we use these cascodes? They are actually used very widely in integrated circuits. Let us start with a current mirror, which is used as a current source. If we have a current I naught, the output current nominally is also I naught. Let me terminate the output with a voltage source, V term, and this current is also I naught. Now, we know that the current is also influenced by the drain source voltage of the transistors. So, the drain source voltage of M0 and M1 could be different, and this current I1 will really be equal to I naught times 1 plus lambda VDS1, which is lambda V term, divided by 1 plus lambda VDS 0. Okay. And also you see that this VDS1 is nothing but V term. So, as the terminating voltage changes, the current here changes as well. Okay. Now, this is undesirable. If I want the output to be closer to an ideal current source, I would like to have a higher incremental output resistance for the current source. In fact, the current source would ideally have an incremental resistance of infinity. Now, I know my cascode trick. So, what I will do is take this current and have a common gate structure on top of it. Let me bias it with some Vg0, which will maintain all transistors in saturation region. Or let me call this MC1. Okay. Now, I do know that the current here will not be affected significantly by V term. Okay. If I change V term by, let us say, some delta V term, originally I would get a change of delta V term times GDS1. Now, I will get delta V term divided by the output resistance of the combination, and if I write it in terms of GDS1, it will be GDS1 times GDSC divided by GMC. Okay. Now, this GDSC by GMC is a number that is much smaller than 1. So, the change in current due to a change in output voltage is much smaller than before. Okay. So, this is a better current source, but the uncertainty in this value of the current still remains, okay, because this current I1 is related to the VDS of M1 and the VDS of M0. Okay. It is given by the same formula, where this is not V term anymore, but it is VDS 1. So, this is a better current source in that it is not significantly affected by changes in V term, but it is not equal to I0. Now, how would I make it equal to I0? I already know that the current would depend both on VDS and VGS. Okay. So, I have to make sure that the VDS of M0 and VDS of M1 are exactly the same, then the two currents would be exactly identical to each other. Okay. Now, how do I arrange for that? Let us go back to how we came up with the diode connected arrangement. The way to think about this is that you are subtracting the current ID from the desired current I0 and applying a negative feedback to the transistor, and the transistor is a transconductor. If the gate voltage increases, if the voltage at this node increases, the current here increases, okay, and that tends to lower the voltage, and finally the circuit reaches equilibrium when ID is exactly equal to I0. Okay. Now, let us say that I have a transistor and I use a cascode transistor on top of it. If you look at the behavior between these 2 points, how it responds to voltages here, what happens now? If I have an increment VGS applied to the gate of M0, I will have an increment GM0 times VGS. It is exactly the same as what I would have here. Okay. If I had an increment VGS here, I would have an increment of GM0 times VGS. The only difference is that this MC0 will improve the output resistance of this combination. Okay. This is at some VG0. Now, I can use exactly the same structure with the cascode combination. I subtract whatever current is flowing here ID from a reference current source I0, and I know that the current ID is controlled by this VGS. So, if ID is more than I0, this voltage is smaller, and if ID is less than I0, this voltage becomes larger. So, I complete the feedback loop like this, and this feedback loop also is stable when ID is exactly equal to I0. Okay. Otherwise, this voltage will be either increasing or decreasing and the circuit will not reach steady state. So, what is the difference between this circuit and that circuit? In the circuit on the left side, ID equals I0 and the VDS of M0 equals the VGS of M0. Okay. Whereas, in the circuit on the right side, what is the value of VDS of M0? That is equal to the gate voltage of MC0, that is VG0, minus gate source voltage of MC0. Okay. Now, the key point here is that this VDS is independent of VDS of M0. Okay. So, therefore, it can be independently adjusted, and earlier I said that I wanted to make the VDS of M0 equal to the VDS of M1. Because I have an independent knob to adjust the VDS of M0, I will adjust it such that I have exactly the same VDS for the two transistors. Okay. So, let us go back to that circuit. Let us say I connect some VG0 over here, okay, and I do by biasing by connecting a feedback to the gate of M0. The current here will be ID equal to I0, and also the VDS of M0 will be VG0 minus VGS of MC0. Okay. Now, let us say here to the gate of MC1 I connect a voltage VG1. What will be the VDS of M1? This is VDS of M0. VDS of M1 will be VG1 minus VGS of C1. Okay. By the way, I have to add the currents here. VGS depends on the current. So, this is VGS C0 at a current of I0 and this is VGS C1 at a current of I1. Okay. Now, let us say I want a 1-to-1 current mirror, that is M0 and M1 are identical and I want I1 to be equal to I0. Okay. So, then it is very obvious that if I make MC0 and MC1 identical, they will have the same VGS at a given current. Okay. So, I will bias these two voltages from a common voltage VG0 that I will obtain from somewhere, and now M1 and M0 are identical to each other, MC1 and MC0 are also identical to each other. Okay. So, under these conditions you can work out that the VDS of M0 and VDS of M1 are exactly equal to each other. So, I1 will be equal to I0, okay. VDS1 and VDS0 are equal to each other. So, I1 simply equals I0. Okay. Also, MC1 is a cascode transistor for M1. So, any change in this output voltage V term will cause only a very small change in the current. So, it is a better current source as well. Okay. So, this is known as a cascode current mirror. This structure is a cascode current mirror. Okay. And it has greater accuracy because the VDS of M0 and M1 are matched to each other. It also has a higher output resistance. So, overall it is a much better current mirror than the conventional current mirror that we had been using all along. Okay. This is also a very widely used circuit to generate accurately mirrored currents. Okay. The only thing now is to determine the value of VG0 such that all transistors remain in saturation. This is a precondition because M0 and M1 have to remain in saturation, they have to behave like current sources, and MC0 and MC1 also have to be in saturation, because if the cascoding has to be effective, its GM times RDS product has to be a much larger number than 1. Okay. And for that to happen, it has to remain in saturation region. Okay. So, all transistors have to remain in saturation. This is my cascode current mirror. Instead of a single transistor, I will use 2 transistors in each path, and this is connected to some bias voltage VG0. Okay. M0, M1, MC0, MC1. Now, I am talking about a 1-to-1 current mirror. So, M0 and M1 are identical to each other and MC0 and MC1 are identical to each other. Okay. Now, what should be the value of VG0? First of all, the current source in reality will provide a constant current regardless of the voltage across it. Okay. The IV characteristics of a current source would be something like this. In reality, it will have some voltage range beyond which it will not behave like a current source. In this case, what is the value of V term beyond which this will not behave like a current source? That will be when MC1 enters triode region, that is V term goes below VG0 by 1 Vt. So, if you look at VG0 minus Vt and the voltage is below that, what happens is that above this it behaves like a current source and below this it will do something, and the current will go off to 0 when V term is 0. Okay. In our case V equals V term. We would like this circuit to behave as a current source over as wide a range as possible. So, that means that we should keep this Vg naught minus Vt to be as small as possible, which is basically Vg naught to be as small as possible. Okay. Now, how small can Vg naught be? As Vg naught reduces, these two voltages follow Vg naught. Okay. If you think of this circuit with Vg naught as input and the source of MC1 as output, it is a source follower or a common drain amplifier. Okay. So, this voltage will be below Vg naught by 1 Vgs. So, if Vg naught keeps reducing, the Vds of M0 and Vds of M1 keep on reducing and they will enter triode region. Okay. Now, we know that we have to have at least some Vd sat 1 at a current of I0 across these transistors. Okay. These numbers are equal because we have used identical transistors and identical currents are flowing through them. So, Vg naught has to be greater than Vd sat 0 at a current of I0 plus the Vgs of MC 0, which in turn can be written as Vt of MC 0 plus Vd sat of MC 0. Okay. So, that is the minimum value possible for Vg naught without driving any transistor into the triode region, and that is the value we must use if we want to maximize the range of the current source. This range is usually called the compliance of the current source. So, to maximize the compliance, we should bias Vg naught at the lowest value possible, and the lowest value equals 1 threshold voltage plus 2 saturation voltages. Okay. And how can we generate this? Because the optimum value is a threshold voltage plus 2 saturation voltages. They can be obtained by using a MOS transistor. Okay. In fact, you see that this is of the form of some let me call it Vtx plus Vd sat x, okay, at some bias current. So, I pass a bias current I naught through a transistor which is sized so that its Vd sat equals this Vd sat x. Okay. In such a case, the voltage across this would be Vtx plus Vd sat x, and that is a suitable way of generating Vg 0. Okay. Here I will simply say that Mx is suitably sized to keep M0, M1, MC0 and MC1 in saturation. Okay. Now, you can figure out the size based on square law, you can calculate the size. Now, transistors do not necessarily follow square law. So, in that case you have to maybe with a little bit of trial and error adjust the size of Mx, so that you get the voltage that you want for Vg 0. Okay. And such a structure is also known as the high swing cascode, because the compliance is the maximum that it can be. We can choose a larger value of Vg 0 and the circuit can operate properly, but the compliance of the current source will be smaller than what it could be. Okay. So, this is known as the high swing cascode current mirror. Now, this is not the only way to generate the bias Vg 0. there are many ways which you can look up in the literature. I will just illustrate another way of doing the same. This is my cascode mirror, and this voltage is nothing but the VGS of M0, which is of the form of the threshold voltage plus VD sat of M0. Okay. Now, what we need for VG0 is a threshold voltage plus 2 VD sats. Okay, VD sat of this transistor plus VD sat of that transistor. Okay. So, another possible way of getting the biasing arrangement is to connect a resistance R, so that there is some drop I naught R. I will adjust it to be of a sufficient value that it is equal to the VD sat of the upper transistor. So, the total voltage that we get at this node will be the threshold voltage plus VD sat of this transistor plus some voltage which is roughly equal to the VD sat of that transistor. So, if I connect it up like that, I can have my cascode biasing without using an extra branch. Okay. Previously, I used an extra branch to generate VG0, so this is better. Now, the disadvantage of course is that the drop between these two voltages is given by I naught R, and it relates to the absolute value of the resistance, and that is not very precisely fixed on an integrated circuit. Okay. Because of that, there is some uncertainty. You have to make sure that over all possible variation of this voltage drop I naught R, the transistors remain in saturation region. Okay. So, there are many other biasing techniques that you can think of to bias the cascode, but the main take home message is that you can bias it such that the compliance of the current source is maximum, and that the cascode current source offers a very high output resistance. Okay. Now, a couple of exercises for you. I earlier said that the VDS here and there will be exactly the same and will be independent of V term. Okay. The VDS of M0 will obviously be independent of V term, but what about the VDS of M1? So, calculate the change in VDS1 due to a change in V term. Okay. Change delta V term. This is quite a simple calculation. You should be able to use small signal techniques to do this, and you can see whether my assumption of this VDS being exactly the same as that is justified or not. Okay. Because in reality the current in the left side and right side will be exactly equal only when this voltage and that voltage are equal and this and that are equal. Okay. Now, what we have made sure is that the VDS of the bottom transistors are more or less equal to each other. What happens due to change in VDS of the upper transistor, that you calculate from this one. Okay. The second thing is, please calculate the range of VG0 so that all transistors are in saturation. We have already partly done this. You can also calculate the upper limit for VG0. Okay. So, that is about the cascode current mirror. It offers a very high output resistance, and we can use it in conjunction with common source amplifiers as well to obtain a high resistance. Okay. Now, in general, if we have a common source structure, by that what I mean is we have the source to be grounded, and I can apply some voltage to the gate, whether it is a signal voltage or a bias voltage, and I use another common gate transistor on top of it. This compound transistor can be thought of approximately as a single transistor with a very high R out, very high output resistance, or equivalently a very low output conductance. This is a very useful view. while synthesizing circuits, because we are putting more transistors. It looks like a very different circuit from before, but you can think of this combination as a transistor by itself. We know that the transistor is a voltage controlled current source. If I apply Vi here, I get Gm times Vi over there. Okay. Now, we also know that now this is the same as what we would have with the single transistor. The incremental current here is Gm times Vi. The only difference is that the output resistance is very high. So, in some ways it is reasonable to think of it as a single device while synthesizing circuits. After we have the circuits, we can analyze the complete circuit, including the effect of these different transistors. Okay. So, how is this useful for our single stage op amp? I have my differential pair, and that contributes a resistance of GDS 1 to the output resistance. Okay. So, as I said earlier, we can think of the cascode combination as a compound transistor with a high output resistance. So, I pass the currents of both M1 and M2. We know that if I have V bias plus Vd by 2 and V bias minus Vd by 2, I will have an incremental current Gm Vd by 2 here and Gm Vd by 2 in the upward direction in the other transistor. I use cascode transistors with both M1 and M2. Let me call them M5 and M6, and the gate is biased to some voltage. I will not worry about how to generate that, but it is biased to some fixed voltage. Okay, I will call that Vg5. Now, it is very clear that the same incremental currents will flow in M5 and M6. Okay, the only difference will be that the resistance looking into the drains of M5 and M6 would be much more than what would be looking into the drains of M1 and M2. Okay. So, this is also a differential transconductor which gives an incremental current of Gm Vd by 2, but with a much higher output resistance. Earlier I had a current mirror. The current mirror contributed an output resistance of GDS 3. Okay. I could use the same current mirror, but we know that the output resistance of the differential pair and the output resistance of the current mirror appeared in parallel, okay, or the output conductances added up. We had GDS 1 plus GDS 3. There is no point improving only one of them without improving the other one. So, we will use the cascode combination for both the load transistors and the differential pair transistors. We know how to make the cascode current mirror. I have to add 2 more transistors. Let me call them M7 and M8, and this is the current mirror, and this is Vg7, which I will connect to some voltage. For now, I will just say that the Vg7 is such that all these transistors are in saturation. Similarly, Vg5 is such that all these transistors are in saturation. So, now I connect the two things together and take my output from there. Okay. I could connect it to a capacitor. So, this is my new single stage op amp with an improved output resistance. what I have done is to use cascode transistors in place of M1, M2, M3, M4 that improves the output resistance of each of those stages. The operation is exactly the same as before. You can go ahead and analyze it completely and you will find that essentially all we have done is to replace each transistor by a cascode. So, that means that any place we had an output conductance, now we have a much smaller output conductance. Okay. So, I am not going to do the analysis further separately for this op amp. Like before, though the circuit is asymmetrical, if we terminate the output with a voltage source V term, the impedance looking up here and looking here will become very small. So, the tail node voltage will be almost 0. So, with that condition we can analyze the circuit very easily, okay, exactly like we did for the single stage op amp with the simple differential pair and the current mirror. So, using that you can analyze the circuit and then find out everything about this particular circuit. Okay. Now, in the quiescent condition, when the two inputs are at V bias, because of symmetry this voltage and that voltage will be exactly the same. Okay. That is, the drain of M6 and M8 will be the same as the drain of M7, and we can use the arguments that we used earlier with the other circuit. If we assume that it is any different, we will come up with a contradiction. So, this voltage will be exactly the same in absence of any mismatch. Okay. So, this voltage will be at VDD minus VSG 3, it is VDD minus the VSG of transistor M3. Okay. Now, I terminate that with a voltage V term is VDD minus VSG 3. So, in the quiescent condition the current here will be 0, and if we apply an increment some current will flow there. Okay. So, if I apply plus Vd by 2 and minus Vd by 2 over here, the tail node voltage will be almost equal to 0. So, the two currents will be Gm Vd by 2 in opposite directions. So, the total current in fact will be Gm 1 times Vd, exactly the same as before. Okay. So, as usual I will use Gm1 to denote the small signal transconductance of both M1 and M2, similarly Gm3 for M3 and M4 and so on. Okay. So, the transconductance is exactly the same as before. The output conductance is a different story. Analysis again is similar to what we did earlier. If I apply an incremental test voltage, and measure the current I test, by taking the ratio V test by I test I can find out the output resistance. Okay. Again it is useful to imagine that the NMOS transistors were ideal, that is they had 0 GDS, and calculate the contribution of PMOS transistors, and similarly assume PMOS transistors are ideal and calculate the contribution of NMOS transistors. Okay. Now, it turns out that the resulting output conductance is a sum of these two. Okay. You can do the analysis separately and then do the analysis together, so that you do not get bogged down by complexity. If I have a voltage V test here, now this cascode combination presents an output resistance equal to Gm8, RDS8, RDS4. It also has plus RDS8 plus RDS4, but I am going to ignore that. Okay. If I had to denote the output conductance, it would be GDS4 GDS8 divided by Gm8. Okay. Now, what happens on the NMOS side? NMOS side it is a similar story to before. First of all, looking from the source of M5, the drain of M5 is terminated by a low resistance. Okay. You can easily verify that the incremental resistance of this combination because of this feedback connection around M3 will be 1 over GM3, and the incremental resistance looking into the source of M5 will be 1 over GM5. The incremental resistance looking into the source of M1 will be 1 over GM1. Okay. So, the incremental resistance looking into the drain of M2 by arguments that we used earlier is approximately 2 times RDS 1. Okay. And the incremental resistance looking in there would be GM6 RDS 6 times 2 times RDS 1. Okay. Again I ignore plus RDS 6 plus 2 RDS 1 terms, they are much smaller than this one. Okay. So, if I apply V test, the current that flows into the NMOS would be V test divided by GM6 RDS 6 times 2 RDS 1. Now, as before, this current gets mirrored in M3 and M7 and also gets drawn into M8 and M4. Okay. So, the total current drawn will be 2 times that, half of it goes into the NMOS side, half goes into the PMOS side, and the total current including the output conductance of the PMOS transistors will give a total output conductance of GDS4 GDS8 by GM8 plus GDS1 GDS5 divided by GM5. Okay. GM5 and GM6 are the same, GDS5 and GDS6 are the same. Compare this to what we had earlier. We had GDS1 plus GDS3. Now we have numbers that are much smaller than GDS1 and GDS3 adding up. So, our output conductance is much smaller. The transconductance is exactly the same as before. Okay. So, this is simply a way of making a transconductance whose output resistance is much higher. So, consequently, the DC gain will be much higher. Okay. This is known as a single stage cascode op amp. Now, it is called single stage because it still consists of a single transconductor and whose transconductance equals GM1. When it is loaded by a capacitor, we have an op amp. The difference is that the output conductance is much smaller than before. Okay. Now, if you connect a resistive load to this, it will not be any better than our simple single stage op amp. Okay. Assuming that the resistance is smaller than the output conductance of a single transistor, whether you use a cascode op amp or whether you use the simple op amp, you will get the same gain because the output load resistance will be dominated by the load that you connect. Okay. So, this circuit still cannot be used with resistive loads, but if you use it with purely capacitive loads, the DC gain will be a lot higher. Okay. Earlier the DC gain was GM1 by GDS1 plus GDS3, which is of the order of GM by GDS of a single transistor. Now, we will have GM1 by this entire thing, GDS1 GDS5 by GM5 plus GDS3 GDS7 by GM7, and this is of the order of GM by GDS squared. Okay. So, if you could get a gain of up to 100 with a simple single stage op amp, you could get a gain of up to 10,000 with this cascode op amp. Okay. Now, this type of cascode op amp where things are stacked on each other. If you look at the cascode structure, you have the differential pair, on top of that you have the cascode, on top of that you have the cascode of the current mirror, and on top of that you have the current mirror itself. Okay. Such a structure is known as the telescopic cascode op amp. This thing is known as the okay. So, it has an improved DC gain. Now, we have to evaluate other things as well, just like we did for the simple single stage op amp, like the frequency response, the non-dominant poles and zeros and so on. We will do that in an approximate way, because already you see that the circuit has become quite complicated. If we put down the small signal equivalent circuit of all these transistors together and then write 8 equations in 8 unknowns or something, we will not get anywhere. So, we will use approximate calculations and our intuition into simple circuits to come up with answers to those questions. Okay. So, firstly, the non-dominant poles and zeros of this op amp. Vg7 and Vg5 are such that all transistors are in saturation region. Okay. As usual, we will evaluate the small signal trans admittance by terminating it with a voltage source. Okay. Now, with every node we will have parasitic capacitors, and this circuit has lot more nodes than before, but the primary parasitic was this one which we call CD3, which consists of CGS3 plus CGS4 plus CDB7 plus CDB5. It is similar to what was before. Okay. And any parasitic at the output of the op amp, okay, such as CDB8 plus CDB6, this could be absorbed into the load. So, this primary parasitic capacitance still remains. In addition to that, we will have parasitic capacitances at these other junctions. For instance, this will be CDB3 plus CDB7, this will consist of CDB1 and CDB5, this will be CDB2 and 6 and so on. Okay. This will be CDB4 and CDB8. Now, what I will do is to ignore all of these parasitics, okay, this, that, that and consider only CD3. Okay. Now, as you guess from the structure, the effect of CD3 is exactly the same as before. If I apply a differential increment to M1 and M2, what I get is a current of GM1 times Vd by 2 in M1 minus GM1 Vd by 2 in M2. Now, the current in M1 gets mirrored by the current mirror and is driven to the output. The current in M2 goes directly to the output. Okay. This was exactly the case that we had with the simple differential pair. As you can see, at high frequencies the current in M1 goes into the capacitor and none of it gets mirrored. Okay. So, we will have the pole and 0 doublet exactly as we had before. Okay. We have a pole at GM3 by CD3 and we will have a 0 at twice that frequency. The 0 happens to be at twice the frequency because this pole affects only one half of the signal, the part of the current that is coming from M1. Okay. So, the effect of CD3 is that we will have a non-dominant pole at minus GM3 by CD3 and a non-dominant 0 at twice that frequency. Okay. The dominant pole can be calculated from the output resistance of the transconductor and the integrating capacitor that you have C. Okay. Now, what about these other parasitic capacitors? That we will not do the exact analysis, but we will try to get a feel for what their contribution will be by looking at a simple cascode stage. So, let me take a common source amplifier which has some V bias plus Vi. So, it has an incremental current of GM1 times Vi and it goes into a cascode device. Okay. And I will assume that this is terminated by some low impedance load. So, the incremental resistance looking up would be, if I call this MC, 1 over GMC. Okay. Now, let us say I have some parasitic capacitance from this node to ground. What will happen? The current gets divided between the input resistance of the cascode and this parasitic capacitance Cp. Okay. So, the part that comes out of MC would be GM1 Vi of S, which is the total current times the ratio given by impedance division, which is GMC by GMC plus SCP, which can also be written as GM1 Vi of S times 1 by 1 plus SCP by GM, okay, GMC. So, there is a pole at minus GMC by Cp due to this parasitic capacitance Cp. Okay. Now, this is expected because at high frequencies all of this current will go there and at low frequencies all of it will go to the output. So, there will be a pole somewhere in the middle and the pole happens to be at minus GMC by Cp. Now, what happens in our cascode op amp? The current from M2 goes through M6, okay, but there is a capacitance here which is CdB2 plus CdB6. So, from here at this node we will get a pole which is minus GM6 divided by CdB2 plus CdB6. Okay. Similarly, the current from M1 goes through M5 and that has the same behavior. So, we have a pole at GM5 by CdB1 plus CdB5. By the way, the small signal parameters of M1 and M2 are the same, M5 and M6 are the same. So, these two poles will be at the same frequency. Okay. Now, the current in M1 gets mirrored and then comes out of M4. Again it encounters the same behavior. There is current division between the GM of M8 and this parasitic capacitance. So, we will have GM8 by CdB4 plus CdB8 as another pole. Now, the effect of this is a little more complicated because it is inside a feedback loop of its own, but it turns out that it creates a pole and some 0 which is related to a similar number. Okay. It is GM7 by CdB3 plus CdB7. Okay. Now, in this case I have used CdB instead of CSB, but in a given transistor CdB and CSB are almost equal to each other. So, for instance, in this case it should be CSB5 plus CdB 1, but I have used some capacitance here. Okay. So, there will be lots of poles and zeros, one for each cascode node, and all of those have to be taken into account while designing the op amp. So, in practice what you do is you simulate the circuit, and the simulator will take into account the effect of all of these things and give you the magnitude and phase, and by looking at the phase margin you can decide whether these parasitic poles are at a sufficiently high frequency or not. Okay. Thank you. We will continue this further in the next lecture.